Welcome to the lecture An Introduction to Large Deviations, and today we will discuss an equivalent version of the upper and lower bound in the large deviations via continuous bounded functions. Also, you will see that it will be also convenient way to discuss or to obtain the large deviation principle for some families of random measures, of measures or random variables. Therefore, this section, the lecture today will call Vardan's lemma. It is the section number 10 in lecture notes. And after that, we will also discuss Brooks theorem. And here we would like to realize the following idea. Let me start from a simple and formal computation. Namely, let's assume that we consider a random variable xi that has a normal distribution n 0, 1, expectation xi has expectation 0 and variance 1, and also we consider a function f that is bounded, a bounded function at the moment, and f is bounded. And let's consider, like in the large deviation principle, a limit epsilon goes to 0, and then we put epsilon logarithm, but then instead of probability, we will write the expectation e to the power f of random variable xi multiplied by square root epsilon. You know that square root epsilon xi satisfies the large deviation principle. We obtained that large deviation principle long time ago, and also we divide by epsilon. And then we want to compute this, we want to see what this limit is, but let me just compute that limit using the density of a random variable xi, and it is limit epsilon goes to 0, epsilon logarithm, and then we have the integral from minus infinity to plus infinity, e to the power, let me say that the function which is here has a normal distribution with parameter 0 and epsilon, and we use the density for that distribution. It is e to the power f of x divided by epsilon, and then the density of the random variable, that is square root 2 pi epsilon, and then you have e minus x squared divided by 2 epsilon dx. And then you should remember the exercise. It was in lecture notes exercise number 3.8, but it says the following. Then when you compute the upper limit of n goes to infinity, 1 over n, so something that goes to 0, and then you have logarithm an plus bn, then this is the maximum between two limits. It is limit n goes to infinity, and this limit is associated with an, or and maximum is with limit for another sequence. Of course, if you have more terms in this sum than in that sum, then inductively you will have just maximum between the corresponding limits. Oh, but actually here you see what you have. You have integration. That at least on the formal level, you can think about that as a summation. Oh, therefore, we can continue, or we can continue the computation that, but at least formally. So here I will put like, will put like to see that it is a formal computation, that it is sum, it is supremum, like equivalent of maximum, x goes to r, and then we will have a limit, and then epsilon goes to 0, 1, so it is limit, and then you have epsilon logarithm e, oh, I'm sorry, 1 square root 2 pi epsilon, and then you have e to the power z power plus z power. It is e to the power f of x divided by epsilon minus x minus x squared divided by 2 epsilon. And then using that the property that logarithm of product is the sum of logarithms, you will have epsilon logarithm of something that behaves like polynomially fast, or like 1 over the polynomial. And so actually I want to say that you have the epsilon, and then here you have logarithm of this term, but you know that logarithm of that term goes to infinity slower than epsilon goes to 0. Therefore epsilon multiplied by the logarithm of that in the limit is equal to 0. But then when you write plus and then epsilon, you will have the logarithm and then e to the power, to that power here. What you see that logarithm and an exponent will kill each other, and then you will see this epsilon that is multiplied by the function here, and you see the epsilon in the denominator. So that, and then you will see the cancellation. Therefore, the result which you should obtain here, it is supremum x goes to r, and then it is f of x minus x squared divided by 2. And what it is for this particular case, for the normal distributed random variable, it is f minus the rate function, because this is the rate function for the random variable, or for the large deviation principle, for normal distributed random variables. So therefore, it is supremum of x goes to r, and you have f of x minus I of x. Oh, and at least this homework, these formal computations gives us the hint what we have to obtain. We have to obtain that considering this type of limit for functions f, you should expect to have this type of supremum. If our intuition about the interchange of limit and the integral is correct. And our next statement, it will be exactly about that. We will show that if functions f are continuous functions and also bounded above, then actually this equality is true. It is lemma 10.1 due to Varadan. That says that let psi epsilon satisfies the large deviation principle in a metric space E with rate function I, with rate function I. Then and also, I'm sorry, and also and a function f that is a function from E to R, from that metric space to R, be continuous and bounded above. Be continuous and bounded above. Then one has that the limit which we considered before, epsilon goes to 0, epsilon logarithm the expectation of e to the power rf of psi epsilon divided by epsilon. This limit we also will denote by lambda f, because you see that it depends on f, and later in Brook theorem it will be used. Actually, this function will appear. Then this is equal to supremum. So limit exists, and it could be equal to plus infinity. And that is the expectation of over e of the function f of x minus rate function. Exactly what you see, what you saw before so during these formal computations. And our goal in the first part of this lecture, okay, let me recall that in Varadhan lemma we consider a family of random variables that satisfies the large deviation principle in a metric space E with rate function I, and there is given also a function f that is continuous and bounded above. Then we have that the limit considered before, it's indeed the supremum of the function f minus I. And our goal will be to prove this lemma, and we will start from lower bound. For that, we will fix x, and also fixing x, we will consider an open ball, and also let G. It is an open ball of radius r with center at x. B, then open ball. And then we estimate the limit, the considered limit from below. So it is, at the moment we are not sure whether the limit exists, therefore we will consider lim inf, and we'll estimate it from below. E to the power f of psi epsilon divided by epsilon. And then, of course, that everything will be, we get some, so everything will be, I mean, this is the larger than the same expression, but when we will put here the indicator of the set G, and we will do that, then it is larger or equal than larger or equal than lim epsilon goes to 0, epsilon logarithm the expectation e to the power f psi epsilon divided by epsilon, and then we have the indicator that psi epsilon belongs to G. And now, since we know that psi epsilon belongs to G, we can estimate this term from the below by the infimum over all points y from G. So we will have the following. It is larger or equal than lim epsilon goes to 0, epsilon logarithm the expectation, and then this exponent which is here, it is exponent of psi epsilon, but you see now this expression is not 0 only when psi epsilon belongs to G. Therefore you can estimate this by infimum over G. It is infimum over G e to the power f of say y divided by epsilon. Here y is taken from G, and then you have the indicator function. But now this is a constant, is independent of xi, and you can move it outside of the expectation, and we get expectation of the indicator function. That is the probability. Then we will write it, lim inf y over g e to the power f of y divided by epsilon, and then the probability that psi epsilon belongs to g. But here we have the logarithm of product of two constants. Therefore, we will get, or two sequences. Therefore, we can write that logarithm as the sum of logarithms. We will do that, and then use the lower bound for large deviations. It is epsilon logarithm. And then, by the way, this infimum, that is, you can move inside the exponent, because exponent is a monotone function. Then we have e to the power 1 over epsilon infimum over g of the function f. And then it is that one, and then plus epsilon, and it is logarithm the probability psi epsilon belongs to g. But now this term here, it is just infimum g of f. Therefore, this lim it inf it is just infimum over g of the function f minus limit epsilon goes to 0, lower limit, and epsilon logarithm the probability that psi epsilon belongs to the open set. But we know that psi epsilon satisfies large deviation principle. Therefore, we know that this limit can be bounded from below by the infimum of by minus infimum of I'm sorry, it is plus, but minus infimum of the rate function over the set g, or it is infim g of the function f minus infimum I over the set of so minus infimum over I, and then we can continue because you know that the rate function is non-negative, therefore not I'm sorry, you know, actually not here is you subtract infimum, but if you take and infimum over the set g, but the set g is a ball with center at point x. So therefore, when you replace this infimum but by just a value of function I at the point x, you will get something larger, but here is minus, therefore you will get something smaller. Therefore you can continue, and it is larger or equal than infimum of f over g minus I of x, because x belongs to the set g. Let's point that out, that once again that this limit can be estimated from below, but by such an infimum. But you remember that g it is the ball of radius r, where r it's any positive number. We can make this r going to 0, and since the function g is since the function f is a continuous function, you get that the right hand side will converge to f of x minus I of x for r going to 0. Since the left hand side doesn't have any r here, you see that this limit that is not changed when r goes to 0 is larger or equal than this expression. Therefore, we obtained that for every x from E, we have that lim inf epsilon goes to 0, epsilon logarithm, the expectation f of psi epsilon divided by epsilon is larger or equal than f of x minus I of x. And since it is so for every x, the inequality also is satisfied for supreme over x. Therefore, it implies that lim epsilon goes to 0, epsilon logarithm the expectation, oops, I'm sorry, here should be e to the power, right? E to the power f of psi epsilon divided by epsilon is larger or equal than supremum, and then supremum over e f minus I. That going back to the formulation of lemma, you see that that this limit has to be equal, but now we got the estimate for the limit inf by this term from below. Now our goal will be to consider a lim sup and estimate it from above. It is the second our second part. It will be the second part of the proof. We now prove the upper bound. And to prove the upper bound, here the idea is the following. We will fix n. And first, choose finite many. I'm sorry, finitely many closed set B1 and so on Bm from E. They are not necessarily disjoint. They are any set such that you have that the function f is small outside that set. It is less or equal than minus n for every x belonging to B0 that is the union of sets complement. It is k from 1. Actually, this B0, it is all points outside that set that we choose. And an oscillation of the function on every set bk is at most 1 over n. And you have that the maximal value, supremum, of the function fx on the set x belonging to bk minus infimum x to bk of the function f of x is less or equal than 1 over n for k that is from 1 to n. Since the function f is continuous function and also bounded from above, you can always choose this that family of closed sets with that properties, and this is exercise for you to explain why such a family of closed set exists. And now the idea of proof will be the following, that actually we want our integral, that is the expectation, like here, divide on a finite sums, and then use this property which we have here, because this property is satisfied for the finite sums here. And then we will show that actually a result which we obtain is not far away from the supremum which we have here. Actually, it is our goal, choosing this family of closed sets. Okay, then let's write the estimate. I want to maybe have all computations on one page. Let me go to start from the new page. It is lim epsilon goes to 0, and then we have epsilon logarithm the expectation of e to the power f of psi epsilon divided by epsilon, and then we estimate this by actually what you do, you just add a sum of indicators over all bk. So it is less or equal than lim epsilon going to 0 epsilon logarithm, the expectation, and then you will have the sum, k from 0 to, including that the case 0, to m, that e to the power f psi epsilon divided by epsilon as before, but now you have the sum of indicators, bk. I want to note here that the sum of indicators, that the union of both bk, k from 0 to m, it is a complete space. So, and since, I'm sorry, not both, that closed sets, that sets that we choose. And and when we consider the sum of indicators bk, when we sum k from 0 to m, then this sum is larger or equal than the indicator of the complete space that is equal to 1. So therefore, what we did here we have 1, and we replace that 1 by the sum of indicators, and then move the sum outside the exponent, or exponent move inside the sum, and then we got that expression here. And now you see that we have the epsilon logarithm of expectation, or actually you can move this sum here outside, and then you have the sum of expectations. Let me do that. You first of all have sum, sum has here expectation, and then the sum from 0 to m. And then this upper limit of epsilon of logarithm of sum, it is the maximum. According to the property that we discussed, it is maximum k from 0 to m, and it is limit sup epsilon goes to 0, epsilon logarithm the expectation of e to the power f of psi epsilon divided by epsilon, and then it is the indicator of psi epsilon belong to bk. And then the idea is similar. Before we replaced that exponent by infimum, now we replace that exponent by supremum, and then we get the estimate in another direction, in the direction that we need. It is maximum k from 0 to m, lim epsilon goes to 0, epsilon logarithm, and then it is supremum over the set bk, and then it is at the function f divided by epsilon, and you have expectation of indicator. It is a probability. Epsilon belongs to bk. Okay, good. And now I want to remark that it is less or equal and you see that here we have maximum, and we take maximum over all k starting from 0 to m. First of all, let's split this maximum on two parts. It is a maximum of k from 1 to m, and then maximum with the case k is equal to 0. So this k is equal to 0, we will consider separately. The reason is that b0, it is actually rest of it is just everything what was left after you considered the closed set bk. And with the set bk, we want to work as a closed sets, and we want to use the upper bound in large deviation principle for closed set. And for b0, we will estimate everything differently, because for b0, you see that the function f of x is less or equal than minus n. But here, let me note that actually this term, which is here, it is equal to the logarithm of, you can write that product as a sum of logarithms, and then you will have the logarithm of Oh, I'm sorry again. I made a typo here. It is im. It is here im to the power f psi epsilon divided by epsilon. And then first of all, we can move this supremum inside, and then we have logarithm of exponent. They will kill each other. You will have only supremum. So therefore, that part, it is just supremum. It is supremum of b over bk of the function f. It should be f, right? Of the function f. It is no. Let me just be like do everything step by step. It would be faster and probably easier. It is maximum k from 1 to m, and then we have lim epsilon goes to 0, and then epsilon logarithm supremum exponent, it is just supremum over bk of the function f. Then we will have plus epsilon logarithm the probability of psi epsilon belongs to bk. And then we have maximum the case k is equal to 0. It is also limit epsilon goes to 0. And here also we have supremum, but over b0f plus epsilon logarithm the probability and so on. So it is actually it is not important what is here because we will estimate. And then let me remark that this is negative. Therefore, this part, this whole part, you can estimate by this supremum, but supremum of function f over the set b0 is not larger than minus n. So therefore, this part here, it is less or equal than minus n. This part here, we can estimate using the large deviation principle because the lim sup of this expression is less or equal than minus infimum of the rate function over the closed set bk. Therefore, using the large deviation principle, we have maximum k from 1 to m, and then we have supremum of the function f over bk minus, and then we have infimum of the rate function over the set bk. And then the last, it is maximum minus m. Okay, now we need to do that with the difference of supremum f minus infimum I. But first of all, you see that we choose the closed set bk by such a way that the oscillation of function is not large. Therefore, what we can do, we can replace this supremum by the infimum plus 1 over n. Because you see that when you leave here supremum, move infimum to the right hand side, you will have that supremum is less or equal than 1 over n infimum. Then we have here that it is less or equal than maximum k from 1 to m. And then we have here infimum bk of f minus infimum over bk of the function I plus 1 over n. And then maximum of minus n. So for us in this place, it is indeed important that function is continuous because for the continuity, for the continuous functions, we can build that closed set that oscillation is small, and therefore it allowed us here replace the supremum by infimum. And now I leave that for you as an exercise that the infimum of this function minus infimum of this function, it can be estimated by the supremum of the difference between two functions. Therefore, it is less or equal, that is exercise for you. Thanks. To estimate difference of infimums by the supremum or bk of the function f minus I. Here you have okay. Oops. Okay, it is I, and after that you have plus 1 over n maximum minus n. Oops. And then that supremum can be estimated by supremum of the complete set over the complete space here. So therefore, we get, and that will be written here, that, let me copy that part. We got that that term is less or equal than the supremum over E of f minus I, and then also you have plus 1 over n, and then maximum minus n. And you see that the left-hand side is independent of n. And here you have n, so therefore you can make n going to 0. Oh, I'm sorry, n going to infinity. And then 1 over again goes to 0. Therefore, here this term will disappear. But here you take maximum with minus n. So therefore, when you make n to infinity, this part goes to minus infinity. So therefore, only this part will be left. The supremum of E f minus I. And this implies that limits exist and it is equal to exactly supremum of E of f minus. Okay, we have proved very useful formula. And it is end of the proof. Okay, you see that in one direction, when we have the large deviation principle, then for continuous and bounded from above functions f, you can get that kind of limits exist and is equal to this supremum. And now we are asking, is that true in the different direction? So if you have that formula for continuous functions, then is it true that you will have the large deviation principle? And the answer is yes, and it is the Brooks theorem. It is next theorem. In lecture notes, it is theorem with number 10.4. It is Brooks. And here we assume that we have a family psi epsilon that is exponentially tight. Let psi epsilon be exponentially tight. Right? And the limit, this LF, that is equal to, maybe it makes sense to repeat it, it is lim epsilon goes to 0, epsilon logarithm the expectation of e to the power f of psi epsilon divided by epsilon exists for every f that is bounded and continuous function on E. We just need the existence of limit for every bounded continuous function. It can be equal to plus infinity here, but it has to exist. And then, or minus infinity. I mean, the infinity also here are allowed. Then psi epsilon satisfies the large deviation principle. The large deviation principle with good rate function I, which we have to define here, that is equal to supremum over all f, that is continuous bounded functions. It looks like Fenhill-Legendre transform, but now instead of linear function, you will have the function f. Before in Legendre transform, we had lambda multiplied by x, and then minus the cumulant generating function that now the plays a role this lambda for x belongs to me. Oh, I'm sorry, here is a typo, because you see that in the right hand side there is no x. X has to be here. Thus, this rate function is given by Z supreme. And now let's prove that theorem. First of all, you remember that for the large deviation principle, usually we work with rate functions that are lower semi-continuous functions. And this function here, it is indeed lower semi-continuous function. The reason here is that the function f, it is a continuous function. That is a constant with respect to x. Therefore, fx minus lambda, it is a continuous function, and supremum of continuous functions is lower semi-continuous function. You can prove that, you can consider this as an exercise. It is easy to see that. And it seems that one of homework exercises is exactly that proves that the limit of, that the supremum of continuous functions is lower semi-continuous function. Therefore, let's write that note that I is lower semi-continuous. As the supremum over a family, or supremum of a family of continuous functions, of family of continuous functions. Also, let's note that since a lambda of f is equal to 0, if f is equal to 0, it is trivial, because you see when you take f is equal to 0, then you have exponent to the power 0. Exponent to the power 0 is equal to 1. Oh, once again, if f is equal to 0, then this is equal to 1. The expectation is equal to 1, and then the logarithm of 1 is equal to 0. Therefore, you have limit of 0, and lambda f is equal to 0. Of this, we get that I is non-negative. The reason is trivial, because you have at least one function such that so I of x for every x, it is equal to, so this is equal to 0. it is for the function f0. Therefore, supremum also must be non-negative because supremum must be something something larger or equal than the value for one fixed function. Then you have a function I that is lower semi that is non-negative function. This function is lower semi-continuous function. And we also had a statement when a sequence, when a family is exponentially tight and function is lower semi-continuous, and also the function is good rate function. So therefore, this function I is good rate function. Now we need to show only everything what we need to show that, so we need only to show that the family psi epsilon satisfies the weak large deviation principle. Weak, it means upper bound, bound for compact sets. Because we have exponential tightness, we know that if the family is exponentially tight, then the weak large deviation principle satisfies the full large deviation principle. Oh, therefore, it means that instead of closed set, we can work with compact sets. And now to show the upper bound for compact sets, let's fix first of all we fix then upper bound. So upper bound for compact sets. And let's for that we first fix delta that is larger than 0, and then for every x from E, we choose a function. We may choose a function fx. I put the index x here because it means that first of all I fix it x, and then I choose a function associated with that x using the definition of supremum. Actually, this function has to be such that this supremum is almost realized on that function f epsilon, or fx, I'm sorry. It means that fx of x minus lambda fx, when you put that function, this function will be larger than supremum, that supremum it is I of x minus delta. So you just make step left a little bit. So therefore, according to the definition of supremum, you know that there exists at least one function such that your supremum minus delta will be smaller than the value than this one for that concrete function. Okay, there could happen that this I it is equal to plus infinity. So okay, if I is equal to plus infinity, then you will choose this function such that it is larger than 1 over delta. So therefore, just we will consider two cases together when the supremum is equal to is finite. When it is finite, then you consider minus delta, and you can find that function. If it happens that this supremum I is plus infinity, then we choose this function by such a way that this expression is larger than 1 over delta. Potentially 1 over delta, it is very large, it is very large number because later we will send delta to 0. Also, we recall that function f is a continuous function. So therefore, by the continuity, by continuity, we choose a ball. There exists a ball, an open ball, around the point X, around this, because you see that, okay, you have actually the strong inequality. So therefore, when you consider some points around X, this inequality has to be preserved by the continuity. It is exactly what I want to write. So therefore, you have an open ball such that fx of y minus constant lambda fx, x you remember is fixed, is larger than this constant here, 1 over delta, for every y from that ball. And then also let's note that we have for free the inequality that I will just write using the inequality that that indicator function that psi epsilon belongs to that ball is less or equal than e to the power 1 over epsilon, and here we will write f of x psi epsilon minus infimum of the function fx over the ball with radius x. Let me say a few words why this inequality is trivial. Because you see that, first of all, the right-hand side is always non-negative. So therefore, if infimum is equal to 0, the inequality is satisfied. So therefore, to be sure that this inequality is true, is always true, you only need to focus on, be focused on the case when indicator is equal to 1. But if the indicator is equal to 1, then what does it mean? It means that psi epsilon, you just choose omegas for which indicator is equal to 1. It means that for that omega, psi epsilon of omega belongs to the ball. But if psi epsilon of omega belongs to the ball, then here you consider f of x computed at the point of the ball. But here, from that, I mean from this function, you subtract the infimum over the ball. So according to that, to the fact that infimum actually it is the minimum, roughly speaking, this difference is non-negative. But if the difference is non-negative, then exponent to the non-negative power is something that is larger or equal than 1. So therefore, this inequality is satisfied for any, for both cases, when indicator is 0 and indicator is equal to 1. So we have that inequality, and now using this inequality, we will take the expectation from the left-hand side and the expectation from the right-hand side. Let's do that. I will go to another side. The expectation of indicator will give me the probability of psi epsilon belongs to the ball, and it is less or equal than the expectation of e to the power 1 over epsilon, and then you have fx of psi epsilon, and then it is minus infimum over the ball b with index x, with center at the point x, fx. But you see that this function on the ball is larger than this expression plus that expression. Therefore, when you take here infimum over the ball, this type of inequality will be preserved. It will be larger or equal than this plus that. But you see that the infimum here is taken with minus. Therefore, the inequality will be in inverse direction. It is less or equal than expectation e to the power 1 over epsilon, and then you have fx of psi epsilon, and then it is minus lambda fx minus the indicator of x minus delta minimum 1 over delta. And you see how, but actually our goal is to prove the large deviation principle. And here, what we did here, we replaced this probability by the expectation of e to some power, but in this power you see a function f computed as this psi epsilon. And we know what the limit of this expression is according to the assumption of the statement. So therefore, we can use that. Just let's write that that limit epsilon goes to 0. We have epsilon logarithm the probability psi epsilon belongs to bx, and it is less or equal. It is here less or equal than it has to be upper limit, right? It is lim sup epsilon goes to 0, epsilon logarithm, and then I will copy that expectation. And here you see that something you can easily compute here because you see exponent to this power, but only the randomness is here. That all terms, they are constants. And exponent of this linear combination, it is a product of exponents. But that is constant, and therefore the exponent to this power, you can move outside the expectation. And then you can use that logarithm of product is sum of logarithms. So for what you obtain here, it will be limit epsilon goes to 0. It is epsilon logarithm, the expectation of e to the power fx psi epsilon divided by epsilon. And then you will have minus lambda fx minus I of x minus delta minimum 1 over delta. And you see that we can use that the assumption of the proposition, namely that this limit exists and limit is equal to lambda f. So therefore, we will have just lambda fx minus lambda fx minus indicator of x minus delta minimum 1 over delta. So, and it is equal to minus I x minus delta minimum 1 over delta. Okay, and now just to finish the upper bound, first of all, we showed that for a ball of for some ball we at point x, and we got this upper bound, and now we want to use the upper bound for compact sets when we write here the compact set. But you know that every compact set we can cover by a finite number of balls. So by the way, first of all, I want to say that this estimate you can get for every x from the space E, because here when we fix delta and then we fix S, that was an arbitrary x, and then after that, let K be a compact set. And then let's know that this K, it is a subset of union over all X from E of balls of the corresponding balls with some radius where that radius is defined by this inequality, but it doesn't matter. So it is just open balls for every x, and we have the compact set is covered by a union of open balls. And since the set K is compact set, you know that we can choose a finite subcover. Compact set, then. Oh, and this implies that there exist x1 and so on up to xm from E such that K is a union of the corresponding balls. It is union of I from 1 to m bxi. And then writing the lim epsilon goes to 0, epsilon logarithm, the probability that psi epsilon belongs to k. It is less or equal than lim epsilon. We actually repeat the proof of one of the statements which we had a long time before, or a long time ago, about how having the properties or the estimate for ball, we can get the corresponding estimate for compact sets. And it is epsilon logarithm the probability psi epsilon. Here you will belongs to the union. Then using the sigma additivity, you can write, of probability measures, you can write as epsilon logarithm, and then we will have here the sum. And now you know that logarithm, that this type of limit, it is equal to maximum over all I from 1 to m of lim epsilon goes to 0, epsilon logarithm the probability for balls. And we have obtained already the inequality that is that maximum e from e from 1 to m, from 1 to m, and it is let's go here, it is minus I of xe minus delta minimum, or I think, yeah, minimum 1 over delta. Now you have like minimum. So here you should be careful because it is, of course, that is for the complete expression, right? That. Then here we have it is equal to minus minimum of I from 1 to m, and then is I of xe minus delta minus xe delta. I'm sorry. So here is better to write. I apologize for that. Here we need to take over that. So it is a typo here. Let me write that as well. Of course, what I wrote here, it is correct, but here it is better to write not k, because I will not get what I want. It's better to write the union over k. So of course it is also covered. So therefore here you have that this belongs to k. So the centers of balls belongs to k. Therefore you have minimum as then 1 over delta. And after that, you can say, okay, this actually minimum, which is written here, you can estimate from below by infimum over k, because these xi are from k. And therefore, you will have that this is less or equal than minus infimum of I of x minus delta, minimum 1 over delta. And then when delta goes to 0, we get that this goes to minus infimum. Also here, I'm sorry, it should be k, infimum over k I of x. Oh, and it is how we get the upper bound for compact sets, just using the upper bounds for balls, which we obtained via the fact that we know what this limit is. And now we also need to prove the lower bound, and the lower bound. And for that, we consider any open set G, an open set G and take some element and take element x that belongs to G. Then for each then for each n we can choose a continuous function fn from e to minus n comma 0. This function is bounded. It takes only negative values, but this function is such that at x it takes value 0, fn of x is equal to 0, and fn is equal to minus n outside the set G on G complement. Then what we have that minus I of x it is that is equal to that is equal to, I mean, let's go back to the first statement of the lemma. You have that I, it is equal to supremum of that one. But now let's put here minus. Then you need to put here minus. But then you move this minus inside, and then the supremum will be replaced by infimum. And then you will have minus inside the bracket. But minus inside the bracket, it is the same that you write this minus that function. So therefore, here that one is it is infimum of lambda f minus f of x, and f is in continuous function. But now you see that this infimum, it must be smaller or equal than just this expression for some concrete function. And now we take the function fn. So therefore, this expression is less or equal than lambda fn minus fn of x. But according to our choice of f, fn of x is equal to 0. So therefore, it is lambda of fn. But this lambda of fn, it is equal to lim, and then you have epsilon going to 0, epsilon logarithm e to the power e fn of psi epsilon divided by epsilon. But now you see that we choose the function by such a way that this function outside this set G, it is equal to minus n, or you can write like minus n and then so multiplied by that like the indicator of that set. So therefore here we have that it is less or equal than lim. Epsilon goes to 0, and then we have epsilon logarithm the probability that psi epsilon belongs to G, and then maximum minus n. So maximum minus n, and then when we send, and then if n goes to plus infinity, we get the upper. We get the lower. Oh, it is how we obtained that inequality. And by the way, so here also it is important to write the following remark. I'm sorry. It is 10.5 that states that all results of this of this lecture remains true. True of for a family or a family of for a countable family of random variables with epsilon replaced by an that goes to 0. Well, therefore, also you have the Baradan formula lemma and you have the Brook theorem. There is still 15 minutes left, and I would like to finish this lecture with, first of all, some application of these both theorems that we proved here to some special case when we will change the density of random variables. We will consider one family of random variables which satisfies the large deviation principle, and then we will change the density for the random variables. And then we want to show that we want to compute or find the large deviation principle for this new family of random variables and want to find the precise formula for this new family. Let me formulate this. So first of all, let's make some preparation. Let's say what is the change of density, and then we will formulate the proposition and we will prove it. We will consider here. We will consider a family psi epsilon. Oh, I'm sorry, psi n. So here we want to work with a sequence. Okay, larger or equal than, say, 1. And for this family of random variables, in a metric space, M, and let's define and also consider a function that is continuous and bounded. And then define a new family of random variables. Define eta n by, and you need, you know that to define a random family of random variables, you only need to define distributions of random variables. So, therefore, we define the distributions of this family of random variables as follows. It is just the expectation of e to the power k psi n divided by an, and then you have the indicator of psi n belongs to A. And that is for every A Borel-Meshchev on the metric space E. And of course, this is not, when you write that like this, it can happen that it is not a probability measure, because when you take here the complete space E, then you have that this indicator is equal to 1, and then you will have only the expectation of this exponent, and this expectation must not be necessarily equal to 1. Therefore, to have the probability distribution, you need to divide by this expectation. We will denote that. We will write it Zn when that Zn is equal to just expectation of e to the power k psi n divided by an. And now we want to formulate the statement. We want to know what is the large deviation principle for eta. It will be the following proposition. Proposition 10.6, which states that let let a family psi n satisfy the large deviation principle in a complete separable metric space in with a good rate function I, and also assume that let eta n be as above for k that is bounded and continuous. So it is defined by, it is actually that it is a distribution psi n with also with this additional density. Or I mean, in another words, probably it is true to say that the distribution of this with respect to that has a density which is defined by this form. And then in this case, then eta n satisfies the large deviation principle in E with the good rate function, the good rate function that is given by, it depends of course of k, okay, of x. And this rate function, it is the old rate function minus k of x minus like this k, which is here in the density, and then minus, and then you need also to make this function that is infimum, it's exactly 0. It is, so therefore we subtract infimum. And here is y belongs to E. And you have I of y minus k of y. Okay, then let's and here to obtain this result, we want to somehow combine the results combined of two statements. We want to combine the Varadan formula, and we want to or Varadan lemma, and also we want to combine the Brook theorem. But you see that for Brook theorem, you need the exponential tightness. So therefore, first, what you would like to obtain. So somehow, so here that, I mean, a few words about like the idea of proof. And here our idea would be the following. First of all, we have LDP for psi n. Then we want to go by this by Varadan to the statement about the behavior of this limit for an logarithm and the expectation of functions. Then after that, somehow we want to go, having this inequality, we want to go to the limit of logarithm of the expectation of E of f of eta n, because here it would be easier to use like to work with I mean, when you know when you have this eta n defined as before, it will be easier to work with that type of expression. So therefore we will easily go from that part to that part, and then we will need go back to the large deviation principle according by Brook. It will give us large deviation principle for eta n. And here is a few problems that you see that in this place you need exponential tightness. So therefore, I formulated this proposition in such a way that I have already just having the large deviation principle for psi n, you get the exponential tightness here for free because we had already a statement that if we are in if we have random variables taken values in complete separable matrix space and satisfy the large deviation principle, then this family with good rate function, then this family is exponentially tight. Then therefore here we have exponential tightness for free. So actually here it is at the moment the question. Here we have exponential tightness, exponential tightness. So therefore, actually here we have like to realize this picture fully, we need to prove the exponential tightness for the random variables eta n, using the exponential tightness for psi n. And it is the first step that we want to do. And then in the second step, we will make this connection that we will show how from this one, we can get like that, we can get the existence of limits of that type. And using Brook, we will get the large deviation principle for eta n. I have only 5-6 minutes to the end of this lecture. Therefore, I would like to propose the following. I will tell you a few words how we can get the exponential tightness, or maybe we can do everything. Maybe we can spend like 5 minutes more and then finish completely this proof. Let's try to do that. Proof. And I don't want to skip this result because this result will be important for us in the last lecture. First of all, let's note that psi n is exponentially right? Because it is theorem, just see, theorem 10.4, 6 point, I'm sorry, 6 point. And we want to show that this implies the exponential tightness of eta n. So first of all, let's then for each, then like for beta larger than 0, we can find there exists so some k beta. It is a compact set in E compact such that we have that the limit and goes to infinity. It follows from the exponential tightness. It's actually the definition of exponential tightness. It is an, it is logarithm, the probability that psi epsilon n does not belong to k beta is less or equal than e. And here we will take minus 2 supremum of k absolute value minus beta. Then, therefore, we can now we can compute the same limit for eta n. I mean, this k here, it is different k. That k, it is a compact set, and this k, it is a function which appears here. Then this for k beta, it is lim, just by the definition, it is lim n to infinity, and we have an, we have a logarithm, and then you will have that probability, it is 1 over zn, and then we have the expectation, we will have the density, this e k psi n divided by an, and then we have the indicator of psi n belongs to k complement delta. Oops, I'm sorry, here should be does not belong or belong to complement. Belongs to complement. Then using that you see that here you have a product. Therefore, you can write that as a difference of logarithms. So you have lim n goes to infinity an logarithm of expectation of e to the power k psi n divided by an, and then it is indicator of psi n belongs to k complement minus, and it is you'll write it here, minus an, and then logarithm, and then we have there just expectation without the indicator, e to the power k psi n divided by an, because it is that. You remember that this is, I'm sorry, this is that. Then we continue. Just estimating, we can estimate that expectation by supremum, and this we can estimate by infimum. Therefore, we will come to the inequality that it is a lim n goes to infinity an logarithm the expectation, and you have e to the power supremum k divided by an, and then you have the indicator of psi n belongs to k complement. This, I'm sorry, that should be k beta, right? K beta complement, and then it is the expectation here minus an, the logarithm, the expectation, and you estimate this by infimum or by e to the power minus supremum, okay, of psi n, just k divided by a. And then, of course, it is equal to just using the fact that this exponent you can move outside. You can have logarithm of the expectation of indicator. It is logarithm of that probability, but this logarithm of the probability you can estimate from below. Therefore, you have what? You have minus 2 supremum k minus beta. And here you see that it is logarithm of z product. Therefore, there will be additional term, logarithm of the exponent, that will be actually this term, supremum k. But here you have an, here there you have an, so therefore you will have plus supremum. You can put absolute value of k, and the same term there. For the last term, it will be plus supremum absolute value of k, that it is equal to minus b. So therefore, you see that for this compact set K, you have that this limit is less or equal than minus beta, and it is how you can prove the upper bound the exponential tightness. So this implies that eta n is exponentially tight. And now everything what you want to do, you want to use the Brooks theorem to show that you want to show that actually your eta n satisfies the condition of Brooks theorem, and this will imply that eta n satisfies the large deviation principle, and also you can precisely compute the rate function. Oh, now we will use Brooks theorem. And for that, for Brooks theorem, you remember that you need to show that this lambda, that the limit, the corresponding limit exists for every f that is continuous and bounded. So we take f that is continuous bounded function on E, and we compute this one. We need to show that the limit exists. And this one is lim n goes to infinity, an, and it is logarithm of the expectation of e to the power f eta n divided by an. And this is, just according to that we know what the density is, it is equal to lim n goes to infinity an logarithm, and you have 1 over n, and then it is, oh, I'm sorry, 1 over Zn, and then it is the expectation of E, but that the function f psi n divided by an plus k psi n divided by an. Now use the property that logarithm of product is the product of logarithms, but here you have 1 over Zn, then you will have minus logarithm. It is lim n goes to infinity, an logarithm of the expectation of e to the power f psi n plus k psi n divided by an minus an logarithm, and it is just the expectation of Zn, but it is the expectation of k psi n divided by an. Okay, good. We have this, and then let's use, and you see that now we can use the Varadhan, we can use the Varadhan lemma for psi n. And in the Varadhan lemma for psi n, we know what that limits are. That limits are, for the first term, it is supremum over x, and then you have here exponent to this power. This function is continuous and bounded, so f and k is continuous and bounded, and therefore you have supremum f of x plus k of x minus the rate function. And then you have minus, and then you have supremum over x, and then you can have k of x minus I of x, right? Because your function in the Varadhan, so it is in the Varadhan lemma, it is k. So therefore you will have k. Let me just quickly go back to convince you that it is indeed so. You see that in the Varadhan, when you have the function f that is continuous and bounded above, but you have more that it is bounded, then this expectation, it is with the function f here, it will be the function f. So in first case we have the sum f plus k, and in the second we have just k. Yeah. It is that, but now we can combine that a little bit, and we can say, okay, it is a supremum of x, and then we have of that supremum, and then we have f of x, and here we have minus I of x minus k of x. I just put like minus, so in the brackets here. I just put this, and then you have minus supremum. But here I want to write as infimum. It is, I want to put minus, it is plus infimum of x, but here you have I of x also minus chi of x. Good. And you see that actually what is written here, it is a constant. That is constant. Let me write that in just like that. It is constant. And then you take this constant and put it inside the supremum. The supremum will not be changed. And then what you will have? You will have the function f minus this complete function. So, but that function, you see that we denoted that function as follows. We denoted that, so this minus infimum, it is exactly ik. So therefore, maybe it makes sense to write this once again to make that more clear. It is supremum over all f. Let's to be more clear, let's delete that x. So it is like we will have that it is like infimum I minus k. It is a constant. So therefore, supremum of f of x minus, and you have I of x minus k of x, and then you have you put z minus outside, so therefore here you will have minus infimum I minus k. But this is exactly supremum x f of x minus minus ik of x. And then I want to leave the exercise, this as an exercise for you, that you see that this expression, it is equal to the supremum of this. And it is exactly the expression that you would see in the Varadhan lemma for the random variables eta n if they satisfy large deviation principle for this rate function. So therefore, now for you as an exercise, it will be, and in the lecture notes also it is formulated like as an exercise, and I will give you that as an homework exercise, where you have to show, where you have to precisely compute the following. You see that in the Brooks theorem, the rate function is defined like this type of the transformation. So therefore, you need to show that taking this lambda that we computed for random variables eta and putting in here, you will see that you will get exactly the rate function I that coincide with this function that you obtained. So then as an exercise, this implies that actually ik of x, it is equal to supremum over all f belonging to C B of E of f of x minus lambda fk, where this lambda fk, it is what we computed here. So it is exercise homework. That finishes the proof of the statement. Okay, I apologize for longer lecture today. I wanted to finish everything, and next time we will talk about exponential equivalence, and after the exponential equivalence, we will discuss one of the application of large deviation principle in statistical mechanics. It is everything for today. Thank you so much for your attention, and see you in a week.